I forgot to give you some references where you can read about the stuff that I'm explaining. So first of all, what I'm basically explaining here today, the comparison of this quantum reference frame formalism, this perspective neutral framework in relation to special relativity. There's an introductory section on this in section 2 of this reference here. I just give the archive reference from 2 years ago. In that section, we also explain a little bit some of the differences to other approaches. Then I should say that one is actually phrased only for finite abelian groups. For simplicity, that paper that has to do with applications that come later. This general framework for unimodular groups that I'm actually describing on the board is in this reference here from about 4 years ago. That one also has some discussion on the relation between this PN framework and this so-called perspectival one. And then there's this recent paper that came out that's not from my group that actually compares in the essentially simplest possible setup where you have the group to be just Z2 and you're dealing with just a bunch of qubits. But it's a non-technical introduction to the different ideas, conceptual ideas behind the different approaches, including the perspective neutral approach, and then basically showing how they lead to inequivalent descriptions. Okay? So if you're interested, it's a pretty non-technical introduction to that. So in particular, that compares the operational extra particle and perspective neutral approach, this last one. And so it is kind of agnostic in that sense. It's I mean, what they could say, for instance, that of course for gauge symmetries, okay, it's a bit unquestionable which of the approaches we should pick, but it's a bit more written for a quantum foundations audience that doesn't really care so much about gauge symmetries. So I just wanted to put that here. So now I wanted to come again to these quantum reference frame orientation states. So I'm sorry this became a little bit messy here. So again, the part that's written on this side is not the counterpart of this here. It's actually still the counterpart of the first part that I wrote down here. It's just that I didn't have enough space. And sometimes these coherent state examples are just, it's an example, and that's the one that we're going to be using, in which you can actually come up with a covariant POVM. And really, the main thing is that in general, these frame orientation states, or these coherent states, they can be an over-complete basis, so they can be fuzzy. And then this is, for instance, the case. You can convince yourself that then, when they are fuzzy, that these effect operators, they still satisfy all the properties of a POVM, which I've summarized here again. So they're positive, self-adjoint, give a resolution of the identity, they satisfy this additivity property. But when they are fuzzy frames, so it's an over-complete basis, and that's of course typical for coherent states, then you will have that for non-overlapping Borel sets, so measurable sets, that the probability operators associated with them, they don't multiply to 0 in that case. And that comes about because, the overlap of, in general, I will have that, that phi of g and phi of g prime is in general not proportional to delta gg prime, where I'm using the delta function on whatever the V group is. So in general, I will not have that. So meaning, there is some non-trivial overlap between g and g prime states. And that is ultimately the reason why in general, I will have that the effect operators, even though they correspond to disjoint sets on the manifold, or the group manifold, that they don't multiply to 0. So this is allowed, and well, this allows us to do something much more general. Maybe one more thing that I should say is, and we're going to be using them quite often, which is the case that it simplifies things quite a bit. Ideal quantum reference frames, we will call those reference frames such that the orientation state are actually orthonormal. So let me maybe just add that here. So ideal quantum reference frames, this is the case when you have phi of g phi of g prime is just the delta function g prime, where it's the delta function on G, on the manifold G, okay, with respect to the H measure. So if you want, I just add a label down here. I put a G on the delta function. I don't know if you can read this actually. Is this here in the way? Can you read this, or I guess not? So I'm writing basically phi of G prime is delta G prime. Okay, so delta function with respect to the H measure. Okay, so those we're going to be calling ideal quantum reference frames when they have when it's non-fuzzy frame states, when they're perfectly distinguishable. And this is, of course, in that case, you will have that the POVM actually becomes a PVM, as projection value measure. Okay, so much about the general ideas about how to model quantum reference frames, or the orientations. So let me illustrate this now in a concrete example so that this isn't just so abstract. Can I wipe out this part here, because I wanted to keep this a little bit longer, because we're going to be building up on this. No objections so far? Okay. Okay, maybe I should keep this for the moment. I'm going to start with a very simple example. Example 1. So G is just a translation group, and we could have that HR is just an L2 over R. Okay, so a particle on the line. And this is in fact what is called a regular representation of the group R in this case. L2 over the group, that's always that's called a regular representation. And in this case, we could have that UR of G. So G, the group element, we can label by X, right? So because the group is just R, right? So this here is basically our G. It's how far do we translate, and we can have we can represent it like this on that Hilbert space. And well, a coherent state system, I can have. I mean, it's just. Okay, when I say coherent states, I should really emphasize here generalized coherent states. I can have x plus y, so I just take the position eigenstates, and well, this is UR x y. So this is a simple example, and of course these guys, so they satisfy these conditions here. So this would be a quantum reference frame for the translation group. Of course, I mean, they provide a resolution of the identity here, right? By construction, I mean, on this L2 over R. So, so this here is satisfied. That E of R is the identity of R, so that's clear. And okay, it's a projection value measure. I mean, you can tick off all the other things that we looked at. I mean, it works, and also because this is covariant here, it's very easy to check that. When I build these E of X operators in this case, so I would just pick some Borel subset of the real line. It could be some interval, and you want to know what's the probability that the particle is in the interval X. But you would just be looking at this here, and because these position eigenstates transform, of course, in this nice way. I mean, it's a simple exercise to convince yourself that when I conjugate these effect operators by e to the IXP hat, that doesn't do anything else than translating this label capital X. So should I write this down, or is that relatively clear? So this is a very simple example. Now let's do. So this is in particular. This is an ideal quantum reference frame, because of course this property is satisfied. The orientation states are orthogonal. So it's a bit of a trivial example. So we can be a little bit more sophisticated. And so now, in order to describe what I just did, I wouldn't have needed to go to the whole notion of POVMs, projection, positive operator valued matters. I could have described this without it. But I hope that the next example, this is a bit less trivial. This will be about clocks now. And so you can think about them as basically temporal QRFs for, again, G equals, we're going to take the simplest case of time translations. So it'll be, again, the translation group. And we can consider a clock Hamiltonian such that, for simplicity, we don't have to do this, but for simplicity, I'm going to assume this, such that the spectrum of HC, well, let me say that it is continuous and non-degenerate. Okay. Could be the full real line, but it could be less. It could be some interval or something like this. So that it is continuous guarantees that this object, so in particular I will then have, so here when I deal with clocks I usually write R equals C, so reference frame equals clock. So here we can then of course look at something like this. So time evolution of the clock system on, I guess I should again say, we have a clock Hilbert space and let me, so I'm going to call the sigma C the spectrum of this guy, and we can think of this here, for instance, as an L2 over the spectrum of this. So I write it as an L2 over the spectrum of this. It may also be an L2 over R. I mean, how I write it, it depends a little bit on what kind of eigen decomposition I choose, but we're assuming, of course, that this is a self-adjoint operator in the Hilbert space. It is continuous and it's non-degenerate. That means I have a complete basis. Assuming, okay, it's L2 or something, I have a complete basis for this Hilbert space that's given by the eigenstates, the energy eigenstates of the clock. And okay, they have a continuous spectrum. And so that's how I can write it as an L2 over sigma C. Okay, so now what we want to do is we want to define clock states. And one way in which you can define them is simply by integrating over the spectrum of this guy and by just setting this here. So these are the energy eigenstates of the clock. Okay. I can add a phase here, so I can be a bit more general than this, but for simplicity, let me just take the simplest possible choice. And then it's clear that UC of T prime, T, I guess I should put a C in, that this is T plus T prime, right? All I'm doing is, so here I'm throwing this guy here on this object with a T prime. Okay, here when I act on this, I just get an epsilon, of course, instead of HC. And then I have a T prime, and then I'll just translate that T label, so I have this feature. So this is it satisfies this covariance property that we wanted to have. And in particular, we have again that the clock states, we have, of course, that t is now in all of the reals. So this means in particular the clock readings are g equals r plus valued, right? So they're also, again, group valued. So similar to here, that the tetrad is valued in the Lorentz group, and of course here, I forgot to say that, but of course here also the positions are valued. For the position quantum reference frame, they're of course also valued here in the translation group. Now there is of course a difference here compared to this example, because these clock states, I've defined them also for the case that that the spectrum of HC is bounded. Whereas here in this case, P doesn't have to be bounded. Well, it's not bounded actually. So this is a more general description. And in particular, this means that in general, these clock states are not orthogonal. So we have in general, but we have, we just say this, we have that T prime is delta T prime if and only if sigma c is all of R. Okay. So this is then an ideal clock when the clock Hamiltonian is basically just a momentum operator. So otherwise, it should be obvious, but otherwise T prime is not proportional to the delta function, so it is the clock states will be fuzzy. Now you can check by the assumptions that I've made here that you get a resolution of the identity. Okay, I guess I forgot to write what I meant by the effect operators, but it's should be fairly clear. So yeah, okay, maybe let me just write it again. So E of x is, in this case, it may be some time interval. Okay, so this is for the same reasons as before, a positive operator. And when I take E of all of the reals, you can check that this gives you a resolution of the identity on this Hilbert space here, based on the assumptions that I make. That this is a non-degenerate spectrum here. This resolution of the identity in terms of the clock states follows from the resolution of the identity of the energy eigenstates. So I can, of course, I can take this condition here. So basically I set x to be all of the reals. And then for TT, I just insert the definition. So I rewrite the whole things in terms of the energy eigenstates, and you can convince yourself as an exercise that writing E of R amounts to ultimately the resolution of the identity in terms of the energy eigenstates. So that's how you get that there is a that they give you a resolution of the identity, and then by these conditions, okay, this defines you a positive operator valued measure, even for non-ideal clocks, even in the case when this is not true. So you can check again in this case that if you conjugate, it's basically because of this covariance here that we translate the group label in this nice way. If you take these E of x, these effect operators, and you conjugate them by UC, all it will do is really translate x by plus t. Okay? So that's the covariance condition that that we have here. So it's something you can check easily. Sure.
Bounded Hamiltonian is related to also joints.
Yeah. So that's a good question. I was about to come to this now. So at the moment, so this is a self-adjoint operator, but it has a bounded Hamiltonian, and that tells you, of course, that there is no canonical conjugate to HC that is also self-adjoint. Okay, but none of what I've said here is in contradiction with that. So, I mean, these guys here, these effect operators, they're still self-adjoint, but the thing that's missing is basically a clock reading operator. Because, I mean, what is self-adjoint is the effect operators which define probabilities. But something, like here, I can have an X operator and its eigenvalues are its position so-and-so. I will not have a self-adjoint counterpart for non-ideal clocks. But I can, of course, talk about probabilities. And yeah, these probabilities, E of x in this case, they would amount to, when I evaluate them in some clock state, they amount to, what's the probability that the clock reading is, say, in the interval x. Okay? So that's what these probabilities correspond to. And with any probability distribution, I also have moments. And I can still define moment operators for this POVM. And that's the thing that actually, these will not be self-adjoint in general, but they're basically the generalization of the clock reading operator. So, and that's the thing that I wanted to explain next. Okay, okay, maybe I'll continue this here. So, so we can now define the moment operators. So maybe should I write this down? That maybe I'm just going to write it for those that are not so familiar with these things. So this is p whatever phi x is the probability that clock reading in, so suppose x is an interval, in interval x given state. I mean, I said it in words, but in case that not everybody picked it up, it's it's these effect operators that I've defined here. These are, they define a probability measure over the set of clock readings, so the set of quantum reference frame orientations, and well, the Borel measures, it could be an interval, and then E of x corresponds to the probability that a clock reading is in, when I measure that it is in a given interval. Okay, so now I can define the moment operators. I could in principle also do this at the general group level, but I haven't explained that. The moment operators, what they will be is, I'm gonna write it like this, subscript n, the superscript n, and there will be, here I'm actually integrating over the whole thing, and I take t to the n t, okay? So clearly, we have that t0, that's just the identity, that's just the resolution of the identity, that's the thing that we had before here. But when I look at T1, if this was an ideal clock, T1 would just be the spectral decomposition of a clock operator. But and T1 would be actually self-adjoint. So if I have an ideal clock, so ideal clock again, where did I write it? Yeah, ideal clock is when you have orthogonal clock states, then it actually turns out that Tn is just the nth power of the first moment operator, and the first moment operator is the clock reading operator. I mean, this just follows from the orthogonality of the clock eigenstates. Yeah.
When you define the clock state cat t, is there a freedom of adding a weight in there?
Oh, here you mean?
Yeah.
So you can add a phase, something like this here, for instance. That's about it. So I mean, okay, here I'm actually using a uniform measure. So if you're asking about the spectral density or so, then I'm actually taking uniform spectral density here. So if you change the spectral density, you will probably mess up the covariance properties.
So there you are assuming that you have infinite resolution of the time, the clock time.
What do you mean by of the energy eigenstates? You mean, or so the clock? So the resolution of the clock states, I would rather interpret that in terms of the probabilities, and they can be fuzzy, the probabilities. So anyway, so this is for ideal clocks, and plus these guys are self-adjoint in that case. this is only true for ideal clocks. When I have non-ideal clocks, so when these are, when the frame states are not orthogonal, I can still define the moment operators, but they turn out to be only symmetric and not self-adjoint. But I can still use them to define the moments of the probability distribution. So maybe I should say otherwise. So otherwise means, so for the non-ideal case, you have that t to the n is not the nth power of this, and it's not self-adjoint. It's only symmetric in that case. And but one thing that you can show is, I'm gonna wipe this out here. What did I want to know? I just forgot what I wanted to do. I just wanted to write down something, and then while writing out, I forgot what I wanted to write. So, there was something important that I wanted to say, and I completely lost it. Yeah. So, in general, we still have that t, the nth power, and hc. Sorry, remember my comment that if you have a bounded Hamiltonian, that there's nothing that is canonically conjugate to it while being self-adjoint. But you can, of course, have something that is canonically conjugate to it that is not self-adjoint, and that's what happens here. So you can show that this is true. So this is always true under all the conditions that I assumed, so also when the Hamiltonian is bounded. Okay, so in that sense, you have a generalization of the notion of canonical conjugacy. However, now it really involves the full tower of these moment operators. And when the clock is not ideal, then this guy and that guy are not self-adjoint, they're only symmetric operators. So there's no contradiction with the usual Pauli argument. There was this famous Pauli argument that time is not an operator in quantum theory. And basically, one of the arguments was that, if I have a bounded Hamiltonian, there's no self-adjoint operator that's conjugate to it. And that's true, but here, a symmetric one is fine. And the thing is that for us, because we're going to be using these clocks as gauge reference frames, because remember, we're going to treat these group G as gauge transformations, and because they're non-invariant, these properties, these clock states, that means the clock readings are not gauge invariant things to measure, right? So the only thing that will be measurable is the relation of system degrees of freedom relative to the clock, so that the clock operator itself, that parts of it are not self-adjoint, is a priori not even a problem, because it's not an observable directly. But in particular, the probability distributions, those operators are, in fact, self-adjoint. So this is the kind of a summary of how to treat clocks in quantum clocks in the setup. You can also be more general and allow, of course, discrete spectrum and so on, but let me not go into this. So this, I think, comes back also to your question. So you were asking, why should I care about POVMs? So a classic example is if I go to gravity and I have a Hamiltonian constraint, even in mini superspace models, and in general, I will not have a Hamiltonian for the clock that is of the simple form that it's unbounded in both directions. In general, it will be bounded, right? So for instance, I may have that, it could be something like p alpha squared minus the mini superspace model where alpha corresponds to the log of the scale factor or something like this. Then the whole thing here is a bounded object. Of course, a bound from below, of course, it's degenerate, so you have to treat it a bit differently than I discussed this here, but you can also do it with covariant POVMs. And so this tells you immediately that the whole formalism, it doesn't require these idealized clocks, which are very restrictive in Hamiltonian constraint systems. And so it gives you much greater power actually. So that's one example, but this holds in general that you can that these covariant POVMs they allow you to treat really a much larger set of reference frames. And yeah, remember that I said kind of loosely speaking that before when I was discussing the conceptual part, that the quantum reference frame, it should be in some sense as non-invariant as possible in order to resolve gauge orbits. And basically, these covariance conditions, they're the way of formalizing this. So that's a very nice way of formalizing that the reference frame is in some sense as non-invariant as possible, because really the clock or the reference frame orientation states, they transform in the most natural way under the group. Here it's really the group acts on itself with its own group multiplication law, which is true in these Courier states in general. So in that sense, they're in some sense really a kind of perfect orientation states to really deparameterize gauge orbits. So they're very non-invariant. You could have other less idealized or less optimal ways of being non-invariant, but here we're gonna be using those. And really, if you look at the description that I gave you here, I just have to assume there's a Hamiltonian that's bounded, and this will always work, that prescription. So you can always do this. You can also do it for degenerate Hamiltonians. It's just a little bit more complicated, but you can always do it. Okay, so that's the example for clock states. So I hope that is a little bit more explicit than this kind of abstract group business. So this abstract group business is just to let you know that whatever we're going to be describing is not specific to specific examples. It looks much more general. So are there any questions on this example? Otherwise, I'll be moving on to discussing the relationship with special relativity.
Yeah. Will there be any interference between two states?
Interference between two states?
As we are considering a spectrum and defining a state, so if we define multiple states, then will there be like an interference between them?
You mean interference between different clock states, or?
Yeah.
Well, in the okay, I haven't really gotten to that point yet, but I mean in the ultimate gauge invariant states that we're going to be building, they will have support on many clock states in general. If they don't, then in fact I don't really have a notion of evolution. So that will be necessary to have this. But what we will be using in the end is we'll be using these clock states, or in general these quantum reference frame orientation states, to gauge fix or to condition, and then we just use a single quantum reference frame state to condition some observables or some states on the frame being in a certain orientation. Okay, then it depends on what the support of the state is in which you're evaluating this on orientation states. Then these interferences may play a role. But we will not see that so explicitly in the formalism. When you do a concrete calculation, then you will have to deal with it. But in the kind of general framework that I'm describing, it's kind of a bit implicit, but it's there. And you also had a question, yeah?
So if I understand correctly, there are two types of quantum reference frames. One is ideal and one is non-ideal.
Yeah, that's one. I mean, there's more distinctions, yes. But yeah, that's.
And let's say you have two quantum reference frames.
Yeah.
Both is not necessarily ideal. How do you compare which is more close to ideal? Or, I mean, is there any quantitative approach how much the quantum reference frames are close to ideal or the ideal?
Okay, yeah, that's a good question. Okay, I mean, you would basically. I haven't actually thought too much about this, but in some sense, you would have to find a measure that tells you how close you are to a delta function orthonormalization. What would be the best way of doing this? I would probably have to think about it. But in some sense, you would, of course, say that you would have to pick a measure that measures how close you are to a delta function distribution. And of course, when you have, I mean, okay, maybe for clocks it's kind of simple. If they're both non-degenerate, the spectra, then it's ultimately then it will basically be the spectral range of the clock Hamiltonian. The one that has bigger spectral range will be closer to 90 o'clock. So if you squeeze the spectral range of the clock, the more you squeeze it, the more fuzzy the frames get. So in this case, it's simple. But if you're asking at this level, then okay, we'll have to. I don't have a good immediate answer to that.
Excuse me.
Yeah.
So you mentioned a little bit about in the Hamiltonian constraint case there, right?
Yeah, so here, oh sorry, I didn't,
Blah, blah, blah,
so by
yeah.
this I didn't mean I only mean the clock Hamiltonian, but this could lie inside, I could have a Hamiltonian constraint that's right at C, and then it could be HC plus
Something.
HS plus maybe HCS or so, and I'm only talking about this piece.
Okay. Thank you. I see. Some a part of that. I see.
Yeah, sorry, by this I still mean the clock Hamiltonian. I haven't actually talked about gauge transformations yet at the level of quantum reference frames.
Okay. I'm confused.
But actually, I will come to it now. So it's a good question that fits with what comes to us. Is there any other question on this?
Just one question. Of course, block state is gives a natural quantum reference frame, but you don't have to think about clock states when you talk about more general quantum.
Yeah, no, in general not. So I mean, this is really just an example for the case that I have I haven't mentioned it if I have a Hamiltonian constraint. So I consider what is generated by it, temporal reparameterizations, and I want to have a quantum reference frame for deparameterizing that. Then we just call it a clock, and that means it will have to come with its own Hamiltonian. And so here, assuming I'm given, or you give me some clock Hamiltonian, then I'm describing you how to build clock states for the transformations generated by that clock Hamiltonian, and then provided there's no interactions, so that this HCS term is not there, then it is a good quantum reference frame for the constraint. But of course, if the gauge symmetry I'm interested in is a spatial one, then I'm not going to use a clock. Or if the gauge symmetry I'm interested in is something discrete, literally in a gauge theory, then I'm not going to use a clock. Right? So if I have QED, then the quantum reference frame I'm going to be interested in is not a clock, it will be a quantum reference frame for U1, essentially. So for U1 valued space-time functions that act as gauge transformations.
In that case, do you get non-ideal case?
Okay, so maybe we'll see that later. So you can. It depends always on how you build the quantum reference frame.
Okay.
For instance, in gauge theories, if you build quantum reference frames using Wilson lines, you can do this. That always ends up being an ideal quantum reference frame. But in general, no. In general, it's not ideal. Any other question? I'm going to wipe this out because now I'm going to continue with the dictionary. All right, so actually, I think I should have, let me wipe this out. There was a step that I should have done before, I'm sorry. It's okay if you wrote it down and you can keep it, but in the order in which I'm going to write things, there's one step that I forgot, which is what are the externally distinguishable configurations. So under the assumptions that we made in special relativity, or this simple special relativity setup, it's just UA and S smooth. So it's with open space-time index, so with open external Lorentz frame index. So this is something that's distinguishable relative to the external reference frame, the external Lorentz reference frame. So here in the quantum reference frame setup, we will distinguish, of course, states and observables. And the states, we're going to be assuming in this mechanical setup that we're given some Hilbert space that we call kinematical, H-kinematical. So this is already using the language of gauge theories, where you start out with kinematical degrees of freedom, and then you quantize them, and then you impose gauge symmetry. So we're going to be assuming that there is a tensor product structure between the reference frame and the system. So RNS And this is of course not true in general. So, so if you do continuum gauge theories in gravity, that's not going to be true. So that's also the reason why the first part here of these lectures are really more about quantum mechanics. It turns out to be true in lattice gauge theories, and it also is true in hybrid settings, such as these observers in the Zitter space, a la Witten and so on. They're also covered by what I'm discussing here. By continuum series where you have where the fields, where the reference frames are fields, this is not covered by what I'm saying here. And then we'll also have you know, some algebras acting on the reference frame in the system. I don't necessarily have to be specific about what these algebras are, but they could, you know, the simplest case would be that AR is just the set of bounded operators on the system and the reference frame Hilbert space. So they're simple von Neumann algebras, C-star algebras. But there could be something more general. You could look at polynomials and also unbounded operators and polynomials, so for instance in Q and P or something like this. So, so it's not necessary that you write this here. That's why I leave this a little bit more general. So the assumption is there is a set of observables on R and S and states in R and S. And of course, the idea is also that both of them carry a representation of the group G that we're interested in here. And we view this here, the kinematical Hilbert space, as the set of states that are distinguishable relative to the external reference frame, whose different orientations are described by transformations by this group G. Okay? And likewise, the observables here. You remember, at the end of the day, we're interested in the set of states and observables that are distinguishable without access to the external reference frame. So what this here is the, these are the externally distinguishable states and observables. That's the assumption. So now comes the thing that I had before. So, you know, the external frame transformations. So as in gauge transformations. Again, here in quotation marks, I'm a bit careful about this. So here it was something like this, and the important thing is that it acts on all subsystems. So, and here, what we're going to be assuming is that, so I already told you that we're assuming that there's a unitary representation of G on HR. So now we will assume also unitary rep US of G on the system. And we're going to be assuming that U of G, that there's a tensor product representation for simplicity. So, unitary tensor product representation. So for simplicity, we're going to be assuming this. Clearly, if I write it down like this here, then we also have, of course, that it's that just like these Lorentz transformations with respect to the external index, this acts on all subsystems. So in this case, R and S. Okay. So this is an analogy, and of course the analog of this here. So basically lambda mu E mu A. So corresponds to URG phi of E equals phi of E. This is covariance of the coherent state system. So that's the analog of this. Now, again, I said that we're assuming a unitary representation. So this means in particular the product representation is also unitary. You can relax this to at least for R and S individually to be projective, but the formalism gets a little bit more convoluted, and so it's maybe not ideal for introductory lectures. I just want to emphasize that you don't have to make that assumption. Now, another assumption that is going beyond it, that is very difficult to go beyond it, is actually the tensor product representation. So a priori, the framework doesn't necessarily rely on the representation of G to be a product. It's just technically extremely difficult to do something when you don't have that. So we have a couple of examples where we can handle this, but doing it at a general level is extremely difficult. And one good example is, again, a Hamiltonian constraint in gravity, or in like a mini superspace model. This here means, for instance, that if we have a Hamiltonian constraint, it means that the interaction term is switched off, right? So the tensor product representation, if we think about the group represented by the Hamiltonian constraint, there cannot be an interaction term, otherwise there wouldn't be a tensor product representation. Now, of course, in gravity, that's in principle a drastic restriction. Right? So going beyond it, again, I mean, it's, in some cases it is possible, but a general discussion of this is still kind of missing. And this, by the way, true, I should say, this assumption is essentially true in all of the approaches to quantum reference frame in the general discussions. In specific examples, okay, as I said, there are sometimes examples where we go beyond this. There's apparently a paper coming up from some of my friends that discuss this also from the perspective neutral approach, going beyond this, but I'm not actually sure if it is at this general level or just finite groups. I think it's only finite groups. But maybe to give you a bit of a flavor why it is difficult to go beyond this, if you do this in gravity and you have interaction terms, it can very quickly switch on chaos. So, for instance, you can look at the Hamiltonian constraint for a closed Friedmann universe with a massive scalar field. That's a chaotic system. And that one has when you have a mass in the scalar field, the mass couples to the metric by gravity, so there's an interaction term, and that coupling turns the system chaotic. It means you can't solve anything in practice. So that gives you a bit of a flavor of why it's difficult to go beyond the tensor product representation at a general level. Because you're immediately going to have like significant difficulties in mathematically actually handling some of these cases. Okay, so that's the so much for the gauge transformations at the moment.
Excuse me.
Yes.
So in general, and under which condition can we drop the interaction term?
Yeah, I mean, for gravity, it's not general, right?
Yeah, of course.
So,
but,
I mean, if you take, for instance, massless scalar fields, it works.
oh.
But massive scalar fields will never work because the mass will always couple to the metric. So.
Sorry, and you were saying in the case of the massless scalar field in any dimension,
Yeah,
it's
because there's a coupling always, right? I mean, if you have a
I
mass,
see.
there's always a coupling. So, I mean, if you go to perturbative gravity, this is fine because you switch off interactions.
Okay.
So, for example, this work by Edward Witten and so on observers in the Zitter space and also in more general settings. This is done in perturbative quantum gravity. Hopefully, we'll discuss that tomorrow. Whatever I'm discussing here applies to that. Okay, so their Hamiltonian constraints are exactly on this form here without an interaction term. Yeah.
Related question, in the Witten's argument, you only need the factorization of algebra, not the factorization.
Yeah.
You only need the factorization of algebra, not the factorization of Witten's argument.
Yeah, okay. Well, but what does the factorization mean here if you don't have factorization there? So I mean, here, of course, I'm using this tensor factor is the same as here.
But in order to get the type 2 polymer algebra, you use factorization of algebra.
Sorry, for a type 2 algebra?
You only need the properties the factorization of algebra.
But so I mean, this type 2 business, my plan was to discuss that tomorrow, but it turns out that this is encompassed by this here. So in that case, in this CLPW story, R would be the observer Hilbert space, and S is the Q of T, the global Q of T. So by Q of T, I mean all the species, including gravitons, everything. So that's maybe one thing that I should add here. So indeed, I mean, everything that I'm saying here, you see, I say a lot of things about the quantum reference frame, but I don't really say anything about the system. I'm just saying there's a system, it has a Hilbert space, it has some observables, it has a unitary representation of the group on it, and that's all I'm going to require. In particular, the system can be a quantum field theory. So the reference frame is not a quantum field. It's clearly, by everything that I've said, it's a mechanical system by these kinds of things that I'm saying here. Because G is a unimodular group, it's a finite dimensional group. So, so the reference frame is, in what I'm discussing here, a mechanical object, but the system can be a quantum field. Okay? And this is exactly what happens in the story of Witten and so on, of introducing observers, where the system corresponds to all the field theory degrees of freedom of all the species that you have in your de Sitter space or whatever space-time background you have in perturbed of gravity. And R is then whatever your observer is. Okay, there's sometimes several observers in the game, in which case the system will also include the other observers. Okay, so it's really the system here I'm treating in quite a general way. I don't really have to make many restrictions on it, except that it has a unitary representation of G.
Let me make sure. So the frames that the probability discussion by with all can fit into the
Yeah.
Great, but probability cannot.
I don't want to go into the details here because we will discuss that tomorrow. So in that case, in Witten's and so on case, again, as I said, I don't necessarily have to assume that AS and so on are, it's just an example. But in the case of Witten and so on, this AS will not be the set of full operators on the QFT, or the global QFT Hilbert space. This AS, for instance, can be the type 3 algebra associated with the static patch. Okay. So then this here is not true in that case. The first line will be true, the second not. But I can treat it. Okay. So it's, but that's something I don't want to discuss now. Let's go into some additional detail. Okay, any other question? Okay. So now we're going to talk about frame reorientations. So, and these act only on the frame. Okay. So yeah, I mean here pictorially, of course, what happens when I do these Lorentz transformations here, really both E and the tetrad and S, both of them will transform. Similarly here, when I do such a gauge transformation, so in the case of translations, R and S will jointly move along the axis. But now frame orientations are going to be transformations that only act on the reference frame, but don't act on the system. And now we can look at, here in this case, the frame index Lorentz transformations. Okay? So this is also an SO31. It's a second representation of the Lorentz group that I have, and it acts only on the frame index. So I can have lambda so I have E mu A, that's mapped to E mu. And of course, S mu gets mapped to S mu because S mu doesn't have a handle for that representation. It's a scalar for the second representation. And clearly, so what happens here in this case is, I'm keeping S invariant. I keep my Lorentz frame, the external one, invariant, and all I'm going to do is I'm going to change the orientation of the red tetrad. Okay.
Physically, what does this mean?
A reorientation of the frame. So I could imagine that.
Is it possible in labo?
I could imagine that the inertial observer who sits in their rockets or so, they're just somehow readjusting their x, y, and including zero. So maybe a very quick acceleration or something like this, an instantaneous one, something like this. But it's a physical transformation. So in particular, so that's important. It's a different representation of the same group that we're interested in. So by construction, it will commute with these guys here. Right? So it's in that sense a gauge-invariant physical transformation. So this here is it's physical. So by construction, commutes with lambda voodoo. Okay, and so now on the quantum reference frame side, by the way, maybe I actually this. So here I've made a convention on the quantum reference frame side. Here what I'm doing is I'm really acting basically from the left. Okay, so if I have you are G prime phi of G, I'm gonna get phi of G prime G in this order. So remember that the group G can be non-abelian, so I have to be careful about the ordering. So this is how we're defining it. So it's basically multiplication from the left. And now what we're looking for is a second unitary rep VR of G on HR that really is a second unitary representation of on the coherent state system. So you can write maybe let's write it as V of G. We write it as VR of G tensor identity on S. So that's the analog of here, right? So this transformation doesn't act on the system. So the quantum analog is that it acts like the identity on the system, and it acts from the other side as gauge transformations. In that sense, it will automatically commute. So VR of G of phi of H, say, then this is a convention, the ordering in which I'm doing this. I want that this is true. Okay. So I'm acting from the other side. So you can say it's in some sense you can say it's an action from the right, right? It acts from the right on the original argument. Strictly speaking, mathematically, it's still a left action. If you are familiar with the definitions of group actions, but maybe let me not go into the subtleties. So let's just call it as an action from the right, but it's not actually a so-called right group action. But the details of this is for what I'm going to say. It's a bit terminological details that are not so important. But so the statement is: this is what we want to have. That on the orientation system, that you have such a second representation of G that acts in this way. And that's, of course, a non-trivial requirement. And not every coherent state system will satisfy this. So there may be cases when the quantum reference frame does not admit any reorientations. Yeah.
You just said the first and the second transformation are the same group.
Sorry, what?
You have two transformations, one is the gauge transformation and another is the physical one.
Yeah.
These two groups should be the same?
Well, yeah, ideally yes, because we're thinking of the quantum reference frame as being. So in general, the answer is no. But in simple cases, it's nicer, it's simpler if that's the case, because we take the configuration space of the reference frame is the group. And the reorientations are supposed to change the orientation of the frame, so it should cover all the orientations. So then the most natural action is if it is the same group. But strictly speaking, it doesn't have to be like this. You're right. It could be that maybe a subgroup only a subgroup of G has a second unitary representation. That is in principle possible. But then it gets into distinctions that I don't really want to go into because that will make things more complicated. But in principle, you could have that. But again, it's also, like I said, we have actually concrete examples also in this, one of the references that I wiped out, where there is none. So there's no such VR of G. So it's only, but there's one, which is the trivial representation that you always have. but that means, you know, for some quantum reference frames that you set up, there's just no reorientations. And, but you can still do physics with that. It's just that the point is again that here, in this case, I mean, by construction again, we have that, you know, VR of G, oops, and UR of G prime, that this is 0 by construction because they act on two separate sides of the quantum reference frame, and this is of course under the assumption that the frame states give you a resolution of the identity that span everything. So then these two actions, V and U on the frame, they commute. So in that sense, you can again think of these frame reorientations as being physical transformations. So just like here, so I'm changing the orientation of the reference frame, but I don't change anything in the system. Really what that does is it changes the relation between the system and the reference frame. That's a physical transformation. And here, for instance, if I'm looking at a translation group example, a reorientation of the frame, so it's an abelian group, it will always exist. It's just immediately given basically by the same representation that I had before. It's basically just given by inverse of UR. So it's like I keep S fixed and I translate R. So it changes the relative distance between R and S. So the relative distance between R and S is translation invariant, so it's a physical observable. But I change the value of it. And it clearly commutes with the global gauge transformations. So in that sense, really it is a physical transformation. And now, in gauge theory and gravity, for example, it turns out that there's this big fuzz about corner symmetries and boundary symmetries, and it turns out, so maybe I will explain that tomorrow or maybe on Friday, these corner symmetries are actually reorientations of the edge-mode reference frame.
I missed something about the relation between station here and then Hamiltonian function.
Oh yeah, no, sorry, this was just it's a bit detached. I mean, so for what I'm writing here, you don't need this. So this was just to give you an example what kind of restriction this is in the gravitational setting, meaning that I want to have a tensor product representation. As long as I have interactions in the Hamiltonian, there's no tensor product representation.
I like to think about the restriction without interaction.
Without interaction?
Yeah.
Yeah, I mean, if I have no interaction, then the transformation generated by the Hamiltonian constraints, because there's just an addition here, I can write it as a product of the clock Hamiltonian, the clock time translation and the system time translation, so it's a tensor product representation.
What is the relation to these cations with that?
Well, so the statement would be that in this case, so if I have CH, HC plus HS, then, so if I do the analog here, then U of t is e to the minus IT, well, CH, and this is e to the minus IT HC times e to the minus IT HS. So it's UC of t, US of t. So it's it gives you a realization of a tensor product representation.
You were omitting the.
Yeah, I mean this is only possible when there's no interaction. Because if there's an interaction, then this is not true. Because then, I mean, then this unitary contains non-locally acting unitaries. So in that sense, it is really a restriction. Yeah. But is that clear? Yeah. No. So I mean, this is just to say that if I have no interaction, then the evolution generated, or the transformation generated, the gauge transformation generated by the Hamiltonian constraint, it is a gauge transformation. It is of this form. So that's one way in which you can realize it.
Sorry, and you said, and CH is a Hamiltonian constraint, right?
Yeah. So I mean,
so and the CH equal to 0 plus?
Yeah. So I mean, we haven't gotten to that point yet, but that is probably the next steps that I will do, because I haven't talked about gauge invariance yet. I've only talked about gauge transformations, and now indeed we want to go to gauge invariance. And then that means I have to pose basically that I solve the constraints. So let me just see the. So we have about 25 minutes, is that right?
Yes.
So
can I ask a small question? So
Oh, yeah.
in some case you put R as a suffix, but in some case you don't. But do you distinguish those kets?
sorry, what was the
Yeah,
question?
the kets can have R, suffix R.
Oh, these guys here.
In some case, but there are some also without R. So do you distinguish?
Oh no, sorry, yeah, that's yeah.
So you should have
They should
R.
all have an R.
always.
I'm
Okay.
sorry. It's yeah, I'm probably being a little bit sloppy here. And yeah. They should all have an R.
Okay, thank you.
So, was there another question?
I have a question about
Yep.
physical transformation associated with reorientation. Does it have to be symmetric system, or it can be?
Oh, you mean symmetry, like in the strong sense that, for instance, the commutes with Hamiltonian or something? Not necessarily. At this point, no. But so it's a more so it's really symmetry in a somewhat generalized sense that it is a transformation at the end of the day that leaves the space of gauge invariant states invariant. So as in, I mean, it acts not trivially on it, but it leaves the Hilbert space invariant. And whether or not it commutes with Hamiltonian is a separate question. So if you have a yeah. So I mean, when you have the case that the Hamiltonian commutes with it, well, that's a special case of reorientation, but in general, it's not necessary. And in particular, also what I mentioned about edge modes and gauge and gravity, it's not always true that these corner symmetries will have to commute with Hamiltonian. Sometimes they do, sometimes they don't. Okay, was there another question or? So then I think, yeah, the next point is gauge invariance really. So, or gauge invariance as in external frame independence, if you remember my terminology. So, so far, here I asked, what are the externally distinguishable configurations? And now, we want to ask what are the internally distinguishable configurations. And we're almost there. So now we want to say what are the internally distinguishable configurations. Okay, so by internally distinguishable, I mean, it has to be gauge invariant or external frame transformation invariant. So here, in the case of special relativity, in the simple setup, they have to be scalars under this external Lorentz group. So so this will be in particular in a. Let me write it like this. Okay, this is the most interesting observable. So there's more. I mean, I can of course have something like this here, but it may be normalized, so there may be no interesting information in there. And I could, in principle, of course, also have so this here is just delta AB. So I mean, this is of course also in principle included, but it's trivial, right? So it's a topological observable. So so these are the internally distinguishable observables, of course, and then all the configurations that we have for these observables, all the values that they can take. When you range over that, that's basically the set of internally distinguishable configurations. So internally distinguishable by the tetrad. And now, of course, the first one is the most interesting one. So when you think about this here, this is a relational observable. Relational, or you can also say a frame-dressed observable. Right? So I have, what am I doing? I'm contracting the 4 velocity with my tetrad. what does it do? It's just describing the 4 velocity relative to the tetrad, right? So this here is, I can call this SA. So the SA components are the components, of course. It's of S along the 4 tetrad vectors. So it's the components of the 4 velocity relative to the tetrad. So, and what are we doing here? We're addressing this non-invariant object, the 4 velocity, with another non-invariant object, which is the reference frame, in such a way that the composite thing is invariant. And the result is describing the system relative to the reference frame. So I'm dressing the bare quantity S with the frame. That's why I can call this a frame dressed observable. And you can also call it a relation observable because it describes the system relative to the reference frame. And so, so this is already kind of suggestive. So I'm using explicitly this terminology. This is, we will see that also in gauge theory and gravity. And in fact, relation observables, dressed observables in gravity will all be of this form here. They have the same structure, of course, adapted to the appropriate gauge group. And at the end of the day, what will also come out of it is that sometimes in literature on high energy physics you hear dressed observables. It's more the high energy physics community. Sometimes you hear relation observables, a bit more the GRQC community. It's really the same thing. So that's why I'm also going to be using the same slash. It's the same thing. So that's one thing that comes out of this work also. Okay. Now, now we have to do the same thing, the analogous thing on for quantum reference frames. And I'm just going to tell you now the basic ideas. So I'm going to throw a little bit the structures at you, and then hopefully in the last lecture I will explain that in detail. Okay. But I want to not go into too much detail now why this works, because it takes a bit of space to explain this, and I don't want to distract from this nice comparison with special relativity. So first of all, also for the externally distinguishable configuration with a Hilbert space and an algebra, and we're going to impose gauge invariance on both states and observables. And this is the core distinction of the perspective neutral approach in relation to anything else. So in particular, we're going to be interested in the Hilbert space. Sometimes it's called the physical Hilbert space. We're mostly going to refer to it as HPN, the perspective neutral Hilbert space. Why it's called perspective neutral, we'll see. And this is basically the, I'm going to write it with a bit of a quotation mark, because what it means precisely mathematically is a bit subtle in some cases when the group is non-compact. It's the set of psi's such that UG of psi is equal to, actually I think I'm probably going to use those slightly different. Let me use round brackets. So round brackets will be physical or perspective neutral states to distinguish them from kinematical states, for which I would use standard angle brackets. And then G and G. So maybe let me put the quotation marks here. And that's why I put quotation marks there. I'll explain that a bit later. But it's basically, so you could say, so when the group is compact, you can literally define it this way. When the group is compact, then the space of invariant states is a subspace of this kinematical Hilbert space, but when the group is non-compact, it is not, and you should think of it in terms of distributions. Okay? There's various methods in which you can think about this, and so that's the thing that I want to discuss separately. Okay, so for the moment, let's just assume there's a gauge invariant Hilbert space, so where I'm actually posing gauge invariance in a strong sense. So it's in the sense of constraint quantization, of direct constraint quantization. So this comes back, I think, to Yuki's question, because you were asking about C equals 0. Yeah, that's of course corresponds to this condition. So if I have a Hamiltonian constraint, and I have e to the I t c h psi equals psi, then that's ch psi equals 0. And again, quotation marks here. So it's the charge. In other words, it's the trivial representation of the group. In that sense, it's the charge 0 sector. And charge 0 means also the constraint vanishes.
I'm sorry, and you are writing HPN.
Yeah, PN is perspective neutral.
Ah, that one.
So the thing is that the perspective neutral approach gives you a new way of thinking about the physical Hilbert space. So physical Hilbert space of gauge theories, the gauge invariant Hilbert space, it gets much nicer interpretation than perspective neutral approach. It will be the space that links all the internal frame perspectives. So that's why it's perspective neutral.
So according to the comment in the first your talk, and that equal H physics equal to HPN holds in if you choose and PN is true, right?
I mean, I'm just defining that.
Yeah, defining.
So
yes,
I just define the physical Hilbert space with the perspective neutral.
Okay.
And, yeah. So you can say you can put a double dot there if you want.
Why did you add quotation mark?
Here.
Yeah.
Yeah, because in the case when G is non-compact. Oh, here. Ah, okay. Yeah, no, I don't know why I put a quotation mark. I mean, this is more like a. Oh, you're asking about this here?
Yeah.
Okay, yeah, that's a bit related to the same thing here because the. Well, I mean, at some level, this is actually true. So let me delete it. I don't want to go into these analyses right now because it's a bit distracting. But it has to do with the fact that when C generates the translation group is non-compact, then this is not an equation on the kinematic Hilbert space because these states are not elements of the kinematic Hilbert space. It's not a subspace. Okay, when the group is compact, it is a subspace. Otherwise, not. But for what I'm discussing, it's not so important right now. So this is the core distinction of the perspective neutral approach that we go. When I said it's the most radical approach, it's that we go to the strongest possible sense of gauge invariance, namely the sense of gauge theories. So that's why at the end of the day you get the smallest state spaces. The physical Hilbert space is the smallest state space that is compatible with the notion of invariance. In other approaches, for instance, you have a weaker sense of invariance, which is, for instance, that density operators have to commute with gauge transformations, which is a weaker condition. And maybe I'll explain that after the break. It's a weaker condition, so there's more states that satisfy this. So, yeah, so this here is basically the space of internally distinguishable quantum states. So, I mean, really we have wiped out every possible external frame information because we treat it as gauge. And now, so formally, you can look at this group averaging projector in quotation marks, which takes you from the kinematical to the perspective neutral Hilbert space. I'm going to be a little bit sloppy here in what I'm writing. It's again it's related to this quotation mark thing, where pi pn is basically just given by dg u of g. So it's a so-called coherent group average, where I take all the gauge transformations. By u of g, I mean this one here. Okay, so ur times us, and I'm integrating over the whole group. Okay, if it's a compact group, you can also you can normalize the H measure, which practice we will do. In that case, it's a so when this is a compact group, this is actually a projector. Okay? When it's a non-compact group, it's not a projector. It's a map from it's a more complicated object, and it's not even mathematically defined to take the square of it, because it's a map from one Hilbert space to another. That's not a subspace. So. So this is a so-called coherent group average. So these are some things that I wanted to discuss a bit more, maybe after the break. That's a little bit. What's the time? So yeah, why we take this more radical step in order to get frame covariance in the end, which I haven't explained yet. Yeah, I hope that I can explain that later today.
The point here is that after projecting so you can just project any state. By this project, you can get a physical state.
Yeah, so I mean, if it's a compact group, then what you say is exactly correct.
Yeah, and then what happens if you have a non-compact group?
Yeah, let me discuss this after the break because that gets into some subtleties. Because it's not a projector in that case. So it's a, and again, this guy, when G is non-compact, this is not a subspace of that. So the whole sense in which you're supposed to think about it is much more subtle. You can think of them as distributions, as gauge invariant distributions on this Hilbert space. So really what it is a map. Okay, it's also defined on a dense subset of this, and it maps to the dual of it. And so let me discuss this later. Okay. So there is a way in which you can make sense of this, but it requires a bit more work, and I will do that later. So for the moment, we just assume we know what this is. Okay, and the details I'll tell you afterwards.
Excuse me.
Yeah.
I want to confirm, just confirm, which is the subspace of H kinematics.
Well, no, that's the thing that, well, so I'm writing it here without the statement that there's a subspace because in general it's not a subspace. So it is a subspace for G compact, for G non-compact. So maybe, maybe let me just write this explicitly so that no confusion arises. So, so G compact, then we have HPN is a subspace of H kin. G non-compact, and HPN is not the subspace of H kin. So we will see later why.
And for the case G compact, H physics are not factorized in
oh, yeah. So, well, it can be factorized, but it's important. Yeah, this is a good point. So this is related to the subsystem relativity that I mentioned in the abstract. The perspective neutral Hilbert space does not inherit the kinematical tensor product structure. Yeah. And that's very important because the kinematical tensor product structure corresponds to a subsystem partition relative to the external reference frame, not gauge invariant. And what we will be doing is we're going to be doing subsystem partitionings of this guy, of the gauge invariant Hilbert space, relative to internal reference frames. And that will become relative.
When have you used the factorization of Hilbert space in kinematic?
Yeah, so that's an input. In fact, I can also relax that. But it requires more technology, so that's why I'm not discussing that. But assuming there is such an external tensor product structure, we'll see how we can get internal tensor product structures using quantum reference frames. So in fact, what we'll be seeing is that when the reference frames are ideal, an ideal quantum reference frame perspective is nothing else than a tensor product structure on the physical Hilbert space. We will see that. It will be later today. So one can make that technically very precise. So this is really, you can think of the quantum reference, so a choice of quantum reference frame, as I mentioned already, it is a split between redundant and non-redundant data. And what I mean by that is really in this kinematic Hilbert space sense. R is going to be absorbing all the redundancy, and then I will have something worse of the size of HS in some sense. That's gauge invariant. It will become more clear later. So it is a split between redundant and non-redundant, and on top of it, it will introduce a gauge invariant subsystem partition. So I've only talked about states here, so now I talked about observables. Let me just finish this and then we have a break. So here, I talked about states, but here really I talked about relational observables, so we need to do the same thing. Let me just start. Basically, we want to have APN, it's AFIS, and really, you can think about it as pi pn times this akin that we had before. So you can think about it this way. But now we want to have something, so it's a little bit abstract. So we want to have something corresponding to these relational observables. And now what we're going to be doing is defining relational observables. So suppose I have some, Fs in As. So whatever As is. Could be a type 3 algebra for quantum fields, or whatever. But I have some observable Fs in this kinematical system algebra As. And I'm going to be tensoring it with orientation states of the reference frame. So what does this thing amount to? So it's a, you can call that an aligned QRF, aligned observable. So what does it do? It measures measuring Fs conditional on R being an orientation G limit G. Right? So when we measure that thing, we're measuring basically this is a conditioning operator, and well, that's the system observable we're interested in. Now this thing is of course by construction not gauge invariant because of the covariance properties of the reference frame states. So we have to turn this into something gauge invariant, and we can define this relational observable right as a function of this. Okay, this is going to get a little tight. Let me leave a little bit more space. I'm sorry about that. So Fs. So I'm going to write it as Fs relative to R, function of G. And we're going to be writing this as dg prime u of g prime dagger. Okay, so this is a so-called incoherent group average. So so we have sometimes. So we're going to be working with this thing here, U of G dagger. This is an incoherent group average. Okay, so I conjugate by U and then I integrate over the group. This is a bit different from this here because here I'm first integrating, and then when I conjugate it something else. So this so the reason I write this is basically that you have any g of a u of g is always going to be 0. So this is you can easily check that. So or maybe put a g prime here, and this has to do with the left and right invariance of the H measure. So there's something you can check in an exercise. It's just using invariance of dg and g relabeling. So maybe I'll leave that as an exercise because it's already pretty late. So this is just to say that these guys, they actually, so this here, so as I mentioned, this part here in the bracket, it's a QRF aligned observable, measures Fs conditional on the frame being in a certain orientation. And then this is also often called the G twirl, this incoherent one. And so the G twirl of this QRF aligned observable is just a gauge invariant version of it. Okay, so this is a gauge invariant way of defining Fs conditional on the frame orientation being G. Okay? So when you think about this here, so to see that this really is an analog of this here, when you think about the special relativity case, what are we doing? So we're dressing the system observable by an object. So you can view this as this is a Lorentz group value. So you can view this as you're Lorentz transforming the system observable by an amount that's given by the frame orientation. That's exactly what's happening here, because we're conditioning on the frame orientation, and by the amount of that, we're going to be gauge transforming. We're just summing over it. And the way to see this is that when I evaluate this on physical states, then the state will have some supports on the frame orientation states. And whatever the support of the state is on the frame orientation states, when this guy here acts on this, it will transform these states, right? And so I'm actually in the end transforming over many frame orientation states, summing over many frame orientation states. But the physical state may only have support on some of them. And so the physical state will tell you by how much, when you act with this, you're actually gauge transforming the Fs. And that depends on the frame orientation. So that's why this is really a quantum analog of this object here. So it's a little bit subtle, but it really is the same kind of object. Okay. So these OFS R of G is a relational observable, or relational, or really a QRF dressed observable measuring okay, I'm having space issues as usual. Okay, I'll just wipe this out. Measuring Fs given that's or conditional really, sorry. Conditional on R in orientation G. So it measures it in a gauge invariant way. Now, here I've used the coherent twirl and incoherent twirl, but actually when I actually sorry, I'm realizing that I should do something else here. I put a G here, I forgot. I should take the G invariant subalgebra of Akin, and then I throw pi pn on it. Sorry about that. So Akin G is actually nothing else than this here. Okay, I should be a little bit. When the group G is compact, this is true. When the group G is not compact, it's not quite true. So I don't really want to get into the subtleties. So the reason is that when you look at this object here, suppose I throw in a gauge invariant object, something that already transforms trivially with gauge transformations. Then conjugating it by gauge transformation won't do anything. This will annihilate this. So I'm just going to be integrating an operator that doesn't depend on G over G. When G is non-compact, it diverges. So in general, this will not converge. So when the group is non-compact. When the group is compact, it will. And then I can do, so I should say if G compact. And G is non-compact, then you cannot define it in this way, but you can define it as the G invariant subalgebra. So in general, I'm just going to define this here as So when G is compact, then this operation will give you the G invariant subalgebra. It actually acts as a projector. This G twirl is actually an algebra projector. It takes the full algebra and maps it to the gauge invariant subalgebra. When G is non-compact, it doesn't quite work this way. It works for frame orientation states, I should say. These divergence issues are not there when you look at these types of observables that are not gauge invariant. But for arbitrary kinematical, you have to be careful if you insert arbitrary kinematical objects here. Okay, now, so one thing I should maybe say is that I'm going to write it slightly differently. So here I put a twiddle on it. So these are gauge invariant kinematical observables. So these guys, they lie in AG kinematical, but I haven't done this projection yet. But at the end of the day, we want to act with these relational observables on this Hilbert space. So I still need to project with this guy. And so they're just going to be this O, Fs, R of G, pi Pn. Actually here I can also, it commutes formally, so I can write it on the left or right, it doesn't matter. So here I'm just going to, yeah, I can, well, no, sorry. No, actually, in order to include the, in order to include the non-compact case, it's actually better to write it the following way, I'm sorry. Because in the non-compact case, if I put the pi Pn on the right, and then I act on physical states, I get a divergence, which I don't want. So this here is pi Pn G, and then I have phi of G are Fs. Here I'm taking the G twirl, so I'm just inserting here these QRF aligned observables. So I have this, and then you can convince yourself that, okay, yeah, this is actually, okay, sorry, I realized I need to do something else. Okay, yeah, no. So this is something that you can check. So this is when you have a combination of pi Pn and G here. This amounts to conjugation by pi Pn, but not doing a G twirl. Okay, so really, what this G twirl does is it super selects, it writes it in block diagonal form across the object that I have inside, across the charge sectors of the group representation, and projecting it once with pi Pn selects the trivial one. Okay, so you get this here. So this is the form of relational observables that we're interested in the end. And okay, so I have this pi Pn here. In fact, I'm sorry, in terms of the notation, really what I want is dropping this pi Pn here, because otherwise it gives me divergence. And when it is compact, it's not a problem whether I drop it or not. It doesn't matter, because I'm always going to act on the image of pi Pn. So in that sense, what I just wrote down here is a little bit, it's not quite what I want in the end. So maybe let's call this here O twiddle tilde, and I'm going to redefine O twiddle. And the ones we're going to be interested in is just pi Pn phi of G tensor Fs without the pi Pn on the right. Okay, so I'm just dropping that. So I have only the QRF aligned observable, and from the left-hand side I have a pi Pn. That's all I'm doing. And so these are the ones that we will ultimately be interested in. So they follow on from these gauge-invariant kinematic observables. So these are gauge-invariant observables on H-kin, on the externally distinguishable Hilbert space. And by these operations of pi pn, I can make this into an operator on HPN. So when I have, when G is compact, then there's no problem in having the pi pn on the right-hand side. But when it is a non-compact group, having the pi pn on the right-hand side is problematic because in that case, I'll have pi pn squared is divergent. Okay? So that's why I don't want to have the pi pn there. So for really it's undefined. For G non-compact. So that's why I'm getting rid of it. But again, so really what I mean by this here is I'm taking these relational observables and I'm restricting their domain to the perspective neutral Hilbert space. So also in the case that G is compact, dropping pi pn, I don't lose any information because I'm always going to act on states that lie in the image of pi pn. So that's why it's always okay to drop it. Okay. Anyway, but writing it in this last line, and that way it accommodates also non-compact groups. Okay, so I've gone over time again. After the break, I'll give you some examples of relational observables. So for instance, what we'll see is if you do this translation group reference frame, so particles on the line, this will, for instance, spit out relative distance observables, for example. So it's just a general way of writing them, but you get explicitly very simple observables. But that I'll do after the break. So we're going to leave it explicit then. So is there any question at the moment? Yeah.
Projectors on for non-compact group case can be well defined within the variety camp, distributional sense.
No, the square is never defined. So I mean, an informal way of seeing this. So what I'm going to write down is mathematically not quite kosher, but it's a way of seeing that you can't do this. So really, I mean, the most precise way of seeing it is that at the end of the day, okay, it's not quite defined on H-kin, it's defined on a dense subspace of it, and it'll map to the dual of that dense subspace, so you have a Richt-Hilbert space construction basically. But it means it takes you from one space and maps it to a dual space. But it means the co-image and the image are not the same, so there's no sense in which I can square it. So that's the most precise way in which you can frame it. In an informal way, you can see this from the definition here. So if I pi pn, if I square it, I can have dg u of g, and I have pi pn, right? So that's what I'm doing. But then this is just dg prime u of g prime. This here is u of g prime, right? And so now what I'm going to do is I'm just going to call this here g tilde, and I can write this as dg tilde u of g tilde by using the left and right invariance of the H measure. Is that clear? So then, so that means I have dg pi pn, but this does depend on pn, so I get here the volume of g, which is infinite if it's compact, so I get the volume of the group times pi pn, and the volume is divergent if g is non-compact. But this is a bit informal, so I mean, okay, it's one way in which you can see that you shouldn't be squaring this in the case for that G is not compact, but it gives you a sense that there's a problem in that case.
Excuse me. So I confused in distinguishing, and you are 3O. And you introduce first O, just small O, and and you introduce O tilde and large or something.
Yeah,
And
so
physically and what are different?
Well, so I mean, you can think of them as being basically the same observables as long as you act on the physical Hilbert space. They're the same. So, so I mean, I can take this object here, this original O, and I can I can represent it on the physical Hilbert space. So since this lies the image of pi pn, I'm basically doing an operation like this here. But really, I have to be careful with this pi pn squared. That's why I have to drop it, the pi pn here. But it's, I mean, let me put it maybe in a somewhat better way. So if I have G, so maybe this helps. So I mean, when I wrote this down, when I started writing this down, I forgot that I end up with something I don't want. That's why I redefined it later. I should have written this maybe in a different way from the start. But basically, this here, this is the original O, this one here. So it's this guy here, right? So I'm just taking this, and now when I act on physical states, you can morally write this as G, so the same thing that's inside, times pi pn, some kinematical state. So angle bracket. And then you can use this thing here as this, right? And so, and then afterwards, so I have then conjugation of the QRF line observable by pi pn. Maybe let me just write it out. So maybe that's so this is pi pn, pi pn. But here I still have the kinematical one, right? So this here is O tilde, FSR of G, but now acting on kinematical states. But now I'm gonna remember that this here is psi, the physical state. So I get pi pn, physical state, which is
Large one.
which is this one.
This is a relation between the three.
Yep. So maybe that makes it clear. So that's why you can also see, you know, if I have a compact group and pi is literally a projector, dropping it or not, it doesn't matter, because I mean this here is always true regardless of whether the group is compact or non-compact. That's why going to this description where I drop the pi pn is always fine, as long as it's understood that I'm acting only on physical states. So whenever I write this old twiddle here, I mean I'm looking at relation observables only on the perspective neutral Hilbert space.
Can I get so?
Sure.
And this is these all are observable. Operators, right?
Yeah.
So and physically, and we think expectation value of the operator is observable, and from that perspective, and which what and the expectation value is physical observable.
Yeah, so I mean you would be evaluating these objects here in physical state. So the expectation values will be defined in terms of the inner product on this Hilbert space.
Okay, it's enough. I
Yeah.
see.
But the thing is that what that inner product is, I haven't really told you yet, right?
Yeah.
Because the thing is, of course, when G is compact and this is a subspace, well, you just take the original inner product. You have to renormalize a little bit by the volume of the group, but otherwise it's the same. But when it's not a subspace, I have a different space, a dual space. I have to define a new inner product on that. And well, hopefully I'll tell you that after the break. Given the speed at which I'm going, maybe I won't. Maybe tomorrow. I'll see. So I mean, so this is why I mean, there's in the dictionary there's a little bit more I want to tell you before I go to making some of these things more precise. So and it may be that the next hour I need to complete the dictionary and then the details come tomorrow. So, okay. But I mean that's the thing that some of these things for the moment you have to take with a grain of salt when the group is non-compact. And how to make it more precise, my guess is probably maybe tomorrow.
And sorry, this is my last question. And do you have any comment about relations to Dirac observable?
These are Dirac observables.
This one.
Yeah.
So I mean more precisely, and how is it related to the one and the Bianca are constructed?
It is construction.
Quantum version.
Yeah.
I see.
So the thing is, so there's a reason why I call them relational observables, because they are relational observables. And they're really the quantization, for instance, of Bianca's power series. And so I can maybe explain that. So of course, for the context where the gauge group is this unimodular group. So for instance, for relational observables, for time evolution, maybe I can explain that after the break. I'm not sure, it depends a little bit. But this is actually how we ended up with this construction here. I mean, I gave you today an intuitive understanding why that's the analog of this thing here, and it really is. And for me, that's the better way of thinking about it. It's not a technical way, but it's a really conceptual way of thinking about it. But the original way in which we arrived at these expressions came from taking Bianca's power series and quantizing it. So it is literally the relational observables, Bianca Dittrich, Carlo Rovelli, but also addressed observables along the lines of what people do in high energy physics. So it's just it's a new way of framing them, but it's a systematic way of building them. So it's and in particular, when you look at quantizations of relational observables in, for instance, the quantum gravity community, what they use is usually ideal quantum reference frames. This is much more powerful because this handles non-ideal quantum reference frames. It's much more general. In particular with clocks, I mean, you can do it for clocks with bounded Hamiltonians, so you get a much larger spectrum of cases you can handle with that.
Thank you.
Any more questions? So if not, then we can. Okay. So let's thank Philipp.